So this is the point where we ended, and physically speaking, our main aim is to calculate this particular amplitude, which is basically the vacuum transition amplitude in the presence of an external source, right? And this is the vacuum at t is equal to minus infinity. This is the vacuum at t is equal to plus infinity, and this is the source. And I mentioned to you in the previous lecture that this function of f of j that we have, this depends on the source j, and this is of the form minus half integral 4 x1 d4 x2 j x2 s function of x2 and x1 j. This is what we have. And I try to motivate why it should be a functional of quadratic functional of j.
এই টার্মটা কি বলে এই যে মানে f of j টা ফাংশনের
এটা আগের ক্লাসে আমি বলেছি। এটা ব্যাপারটা হচ্ছে যে ইট শুড এখন
না না আমি তো ছিলাম কিন্তু
বুঝতে পারেন না, ঠিক আছে। This should be a quadratic functional of j. The reason that I gave in the previous lecture was the following: that you see from this state to this state, you can go via a process where you have to go from 0 minus to 1t. You can create a particle, and then your final destination is 0 plus, right? So you have to destroy this particle. Everything is in the presence of a source, right? So I better put a j over on top. So if you want to go from here to here, you can go directly from here to here without creating or destroying any particles. But if in case if you create a particle, you have to destroy that particle. But each creation or destruction of a particle is associated with a j. Remember? So two j's are involved. That is why you have two j factors. Here, a functional. Therefore, you have to integrate over all the space-time points. x1 and x2 are the space-time points, right? And I put in a function s x2 minus x1. This is my ansatz or assumption, which I want to determine. I will do something now. I will put another physical argument, and my main aim now will be to determine this function. You may say, why is this function required? The very simple answer is physically that this is at x1, this is at x2. So someone should take you from x1 to x2. So you have to put in a function. Now the main aim is to determine this function. This is what you should do. So the way you try to determine this function is you divide this source j into two parts, j1 and j2. Divide it into two parts, j1 and j2. This part of the argument is very crucial. So be very careful about it. So j1 and j2 are two sources, and j1 acts in the causal future of j2. Please write it down. j1 acts in the causal future of j2. What do I mean by that? What I mean is the following: j2 acts first for a certain period of time, and then when j2 ceases to act, j1 acts. বাংলায় বললে সুবিধা হবে। j1 আগে অ্যাক্ট করছে, এই j2 আগে অ্যাক্ট করছে, j2 অ্যাক্ট করে শেষ হয়ে গেল। একটা টাইম ধরো 0 থেকে 5 সেকেন্ড অবধি j2 অ্যাক্ট করলো, j2 বন্ধ হয়ে গেল, 5 সেকেন্ড থেকে 10 সেকেন্ড এবার j1 অ্যাক্ট করবে। So j1 acts in the causal future of j2, and this can be easily done by restricting the support of the functions to suitable regions of space-time. It's a mathematical কথা, but this is actually very simple. Restricting the support of the functions to suitable regions of space-time basically means what I said just before in Bengali, that you restrict J2 from 0 to 5. J2 is non-zero only from 0 to 5 seconds, and so you restrict support ওই অবধি, আর J1 হচ্ছে 5 to 10 seconds. ঠিক আছে? So if you do this, now see, you can immediately write 0 minus 0 plus J2. This is what? This is basically 1 plus. You can write these equations 1 plus FJ2. Because J2 should be at a height, and for J2 it will be 1 plus FJ2. And similarly for 0 plus J1 equal to 1 plus F J1. This follows from this, what I wrote here. Right? So if you do this, now zero minus J, but J is what? J1 plus J2. Let us see how we can write this. Only one thing, some of you may have this confusion. You asked me earlier that whether this is O, this is not O, this is 0. So this thing, you can write it down as, you start from here, 0 minus J2 to 0 plus J2. I will explain this what in a moment. Just write it down, and then 0 minus 0 plus J1. This is what I have. This is my first term, and then plus summation over P 0 minus J2 1P 1P plus. Please write it down. I will explain what this means. So now my aim is to calculate this, is to write this expression. But here J is basically what? J1 plus J2, because I have divided the source into two parts, J1 and J2, J1 plus J2. Now see what happens in the first term, in this term. I said that J1 acts in the causal future of J2. So you may have a situation where you are going from the early vacuum 0 minus in the presence of source J2 to 0 plus, right? Now what happens? J2 ceases to act and J1 takes in. So again, for J1, it is from 0 minus to 0 plus in the presence of J1. This is the first term, right? From this vacuum to this vacuum, প্রথমে 0 minus to 0 plus in the presence of J2, again from 0 minus to 0 plus in the presence of J1. And then,
so in the first case, J2, J1 was absent while it is
yes, yes, yes. That is why I say that J1 acts in the causal future of J2. মানে যখন J2 act করছে তখন J1 নেই, এবার J1 act করা শুরু করলো পর থেকে, causal future এ গেছে. And now look at the second term, this term. Here what happens? 0 minus in the presence of J2, it can go to one particle state, and then one particle state in the presence of J1, it will go to 0 plus, because final destination is this, right? Will be clear? So if you understand this equation correctly, then you can immediately write the following thing. এই ইকুয়েশনে কোনো গন্ডগোল নেই, যদি গন্ডগোল থাকে জিজ্ঞেস করতে পারো, যদি কোনো কনফিউশন থাকে. So this is 0 minus to one particle state in the presence of J2. Now J2 has stopped. In one particle state to 0 plus in the presence of J1, sum over all P, all possible momentum. কারণটা হচ্ছে ওই S টা বার করব, তাহলে বার করতে পারবে। টেকনিক শুধু ম্যাথমেটিক্যাল টেকনিক না, ফিজিক্যাল আর্গুমেন্ট আছে এটা। দিস ইজ দ্য ফিজিক্স। শুধু দেয়ার ইজ নট, see mathematical technique বলাটাও খুব মানে this is unfair, because there is hardly any mathematics here. Mathematics is pure mathematics is much more difficult. Physics we don't even মানে আমরা দাঁতই ফোটাতে পারবো না ফিজিক্স এর ছেলে, বুঝছো? যদি পিওর ম্যাথমেটিক্স বল, this is not mathematics. Algebraic geometry দাঁতই ফোটাতে পারবে, just forget about it. Algebraic number theory দাঁতই ফোটাতে পারবে, কেন করছে কোনো মানে হিসাবই খুঁজে পাবে। So this is just 11 12 algebra, not even 11 12, this is just party algebra, 8 9 algebra, little bit of calculus, nothing else, this is not mathematics.
একটা ছোট অংশ করতে পারি মানে এই সোর্স যেটাকে এরকম অ্যাডিটিভ জি1 প্লাস জি2 করার মানে অ্যাডিটিভ কেন হলো মানে এটা প্রোডাক্ট হয়ে যেতে পারতো না জি1 জি2 নাকি সেটা
না সেটা ঠিক নয়। অ্যাডিটিভ মানে হচ্ছে এটা আপনি বুঝতে পারবেন এইভাবে যে আমার যদি এরকম টাইম থাকে, এইটা টাইম থাকে, এই টাইম থেকে এই টাইম আমি নিলাম J2 which is non zero 0 to 5 seconds, এইখান থেকে এইটা হচ্ছে J1। প্রোডাক্ট কেন হতে পারে না, অর্ডার J স্কয়ার হয়ে যাচ্ছে, আমি তো সব অর্ডার J তে ক্যালকুলেশন করছি। আর আরেকটা ভালো আর্গুমেন্ট যেটা আমি করব, এখন তো সব উইক সোর্সে করছি, স্ট্রং সোর্সে যখন করব I will assume that the strong source is made up of an infinitely large number of small independent uncorrelated weak sources, so we'll just add it up। এই দেখবেন ওর অঙ্কটা একদম সুন্দর করে বেরিয়ে আসবে। এই বেসিক্যালি যেটা হবে একটা এক্সপোনেনশিয়াল আসবে, এই রেজাল্টটা এক্সপোনেনশিয়াল বেরোবে। ওকে, so let us now look at this part. Here it is immediate, the first two terms as a left hand side. Now let us do a little bit of algebra, not mathematics, it's just simple algebra. So let us, what is this term, এই টার্মটা কত তুমি বলো, এই বাদিকটা কত হবে? খুব সিম্পল, জাস্ট একটু সিম্পল, there is hardly anything, এই বাদিকটা দেখলে ওই ইকুয়েশনটা দেখো, এটা দেখো, হ্যাঁ না 1 কি করে হবে, আরো সহজ করে দিচ্ছি, এটা j, এটা দুটো না, এটা j, তাহলে 0 মানে দাঁড়াও ওই বল 0 - 0 + j কত আছে এখানে, কত লিখেছি, কি লেখা আছে বল, 1 f of j, তাই লিখি, ঠিক আছে 1 + f of j, এই তো, আর কি লিখতে পারি, এটাই চাইছি, বাদিকটা বেরিয়ে গেল, বাদিকটা হয়ে গেল ক্লিয়ার। এইবার ডান দিকটা দেখো, ডান দিকটা আমি দুটো ইকুয়েশন লিখে রেখেছি, এইটা আর এইটা। ফার্স্ট টার্মটা ইমিডিয়েট, এখান থেকে উপরের দিকে যাচ্ছি, তাহলে এটা কি হবে, এই টার্মটা কি, fj1, এই টার্মটা কি, ঠিক আছে, এইটা কি, what is this one, 0 - 1p, এটা হচ্ছে I times jp, I times, আচ্ছা এটা j2, have to be careful, j2 I times j2, আর এইটা কি 1p I j1 star, that's it, finished. ম্যাথমেটিক্সটা একদম সহজ, ম্যাথমেটিক্স নেই, পুরোটাই ফিজিক্সই আছে এখানে, এই এটা মাইন্ডসেটটাকে ব্লকটাকে মাথা থেকে হাঁটা, যে ম্যাথমেটিক্স হচ্ছে বুঝতে পারছি না, ফিজিক্সের সাথে কানেক্ট করতে হবে, মাইন্ডসেটটাই ফলস মাইন্ডসেট, there is hardly any mathematics here, পুরোটাই ফিজিক্স। Algebra is very very simple. Now you do this algebra, it is a simple algebra, just multiply these two terms out and see what happens. This is equal to a, এটাকে মাল্টিপ্লাই করলে কত পাবো, we will get 1 plus f j1 plus f j2, very good, and then this term neglect, what are j square, তাহলে দুটো j আছে, 4 j to the power of 4, তাহলে neglect this thing, so I will write this is approximately, right? So for the first two terms, if you multiply it out, you will get this, and then this term is what, minus summation over p j1 star p and j2, that's it. So what have we got, we have got this thing, this is the left hand side, this is equal to that thing, right? So if you simplify this, you will immediately get, if you simplify this thing, the equation that we shall land up to is the following: J1 plus J2 minus Fj1 minus Fj2 is equal to minus sum over P J1 star P J2. That case, very simple equation that you have obtained from these considerations. And now what, so I'm rubbing this part out. Now what we shall do is we shall plug in the answers that we have put. So this is the equation that we have landed up to. Now what is Fj1 plus J2? Fj1 plus J2 is this. Remember the expression for Fj, just see in your notebooks. This is D4 x2 D4 x1. Then it is J1 x2 plus J2 x2 S x2 minus x1, and then J1 x1 plus J2 x1. This was our answers for f of j. So now it is f of j, it is just f of j1 plus j2. So you write this thing down, and then minus of that and minus of that. So minus minus will give you a plus, right? So we'll get half plus half. Again d4 x1 d4 x2. So let me just write this down: d4 x2 d4 x1, and this is for what? J1. So you will get J1 x2 good x s x2 minus x1, and then J1 x1, very good, plus half integral d4 x2 d4 x1. That is what? J2, right? So
J2 x2.
So J2 x2 s x2 minus x1 j
x1.
j x1. So this left hand side is completely done, right? আমাদের ম্যাডাম ফলো করছে সবকটা স্টেপ, so you should be able to follow. আমরা তো বুড়ো হয়ে গেছি, আমাদের ব্রেনের থেকে তোমাদের আরো ফাস্ট চলার কথা। You're sharper than us. You should be able to follow everything. So this is minus sum over p, and then what you have? J1 star p, and then J2. So I just write a dot J2p. So this is the equation that you have, right? Here, all of you. So now what you have to do, I will not do this algebra. This is very simple algebra. Just multiply this term out. So if you multiply these terms here, how many terms will you get? You will get 4 terms. 4 terms. 2 of the terms will cancel these 2 terms, right? It will cancel this part. So if it cancels out, then what we shall get is the following. If you like, you can do the algebra now, or you can do it later. So if you do this algebra, what you will land up with is the following. Let's multiply this and try to cancel these 2 terms out. So 2 terms will remain, and you will get, for the left hand side, you will get the following. So I will write an intermediate step for you, which you will get after cancellation. It will be minus half d4 x1 d4 x2. Then you will get j1 x1 j1 x1 j2 x2 s x2 minus x1 plus j2 x1 j1 x2 s x2 minus x1. So this is the left hand side, right? Clean color. You should be able to get this thing by simplifying these three terms. Simplifying these three. Now the beauty is that these two terms can be combined. Can you say why? S is symmetric in x2. So s x2 minus x1 is same as s x1 minus x2. So this you can show that this term is equal to this term. That is very simple to show, right? By just changing the dummy indices. You can change the dummy variables of integration. You can make this x2, make this x1, then this will become x2, this will become x1, and this will shift. But that is the same as x2 minus x1 once again. So these two terms will combine and what? Half the বেরিয়ে যাবে. I can rub this term out completely. Half is gone. The left hand side and a minus is there. So you'll get this. Okay. And then you have this on the right hand side. You have minus summation over p. So please do this piece of algebra when you go home. So this is minus summation over p j1 star p dot j2. So this is what we have. Now this minus and this minus, this is also gone on from both sides. So this is the ultimate equation that we have landed up to. Now what I shall do is I shall define Fourier transforms. So this I have to do a little bit carefully. Let me just write down one thing. Jx is all of you agree? Students, the Fourier transform of JP. This is Jx. So if you inverse Fourier transform, you have learned Fourier transform, so you know how to invert it, you will get this. Now, there is again a bit of physics here, which most of the textbooks, most of the কোনো textbook এটা বলা থাকবে না. Is something very important. এটাও Fourier transform. Agreed? Plus দিয়েও করতে পারতাম. Plus is also Fourier transform. But now, from physics, I'm using this. This is also Fourier transform. Both are mathematically correct. There is no problem. But physically, I'm going to use this. Physics-wise, I am going to use this Fourier transform, not the e to the power of plus ip dot x. Because the e to the power of plus ip dot x has a different physical meaning. Physically, there is a different physical meaning. It is very easy to see that. Let me just digress a bit, and it also depends on the signature that we have taken. Signature হচ্ছে মনে রাখো mostly negative signature. That is the time component is plus. So if you just shift it contravariant covariant, there is no change in sign. Space part, there is a change in sign, right? So this definition that I'm using here crucially depends on the sign, on the signature that I've taken. Why? What is e to the power of minus ip dot x? I've said in the beginning that p is the fold momentum, but on shell. This basically means minus I P0 x0 plus Pi xi. Einstein summation convention, I have expanded it. But what is P0? P0 is P0 I can take on the top, no change in sign, so metric comes in place. So P0, this is basically P over 0. But P over 0 is omega P because this is on shell. And x0 is what? T plus, and for this term, this is minus pi xi. But minus pi xi, you can write it as p vector dot x vector. Now comes the point, why did I use e to the power of minus ip dot x in the Fourier transform instead of plus ip dot x? The reason is that this corresponds to positive energy. Can you see that why? Why is this Fourier transform corresponds to positive energy? This is a positive energy Fourier transform. It is very easy to see. Quantum mechanics for I del del t, operate with I del del t on both sides. If you operate with I del del t, what will you get? I del t will give you a minus I omega p. So minus I, it is 1. So you will get positive energy omega p. So that is why I'm using this convention. It's a positive energy. So the plus code term with this signature, it would be negative energy. I don't want to do that. And also there is a 2 pi whole to the power of 4 that also has some interesting meaning, but I don't want to go into that thing because I have to digress a lot now. So let's start from this. So if you take this as your Fourier transform, if you invert it, you will get this. And now it is very easy to calculate what this part is. So this part is basically summation over P J1 star P into J2P. So that is basically summation over P. Now for this, I put an integral. What is J1 star? So this will be D4 x1 J1. So this is J1 star x, because I'm taking a star here, and 1, so 1 corresponds to that one, then star, so this gives me a J1 star x, and e to the power of, for this is plus ip dot x, so I will get minus I p dot x1, and this will be x1. Here. And what is J2p? J2p is basically once again d4 x2. This is J2. This is x2 e to the power of minus the plus I p dot. Is that clear? Just do the Fourier transform is samtaতে বসিয়েছি. But in the beginning of my lecture, I said that Jx is real. So Jx is real means this is constant. J1 star is J1. And therefore, that tells us that this can be written as integral d4 x1 d4 x2 J1 x1 J2 x2 multiplied by summation over p. I just put the sum inside, and that will give us e to the power of I p dot x2 minus x1. Is that clear? Very well. So now, if you compare this side with this side, you can determine what is the form of S. S is what? S is basically summation over P e to the power of I P dot x2 minus x1. So our goal is achieved. We have found out what the form of this function S is. So this is the form of this function. Is that okay? So let me just write the form of the function here once again. S x2 minus x1 is equal to summation over P e to the power of I p dot determine. Do you have any questions, students? No questions? Everything is clear or unclear? So, if this part is clear, now I shall do a trick. I shall convert this sum to an integral and write this by assuming that the momentum, they are not discrete now, they are a continuous set of momenta, and therefore you can convert, you can replace this sum over p by an integral over this thing. And what is this d omega p? D omega p is basically d3p by now this part may look like in chess you will often find that if there is a dubious move, there is a question mark exclamation.
Yes.
So this is like a dubious move. Okay. If it is a double exclamation, it means that it is a very good move. But question mark exclamation means that it is dubious. But what I can say is that if you run all the chess engines or your artificial intelligence, it will say that this is correct. It's not dubious. It's perfectly fine. What this basically means is that I told you that this is on-shell momentum. So the energy zeroth component of the momentum is related to the 3 vector, to p vector. So you can realize that if you replace this sum by an integral, it should only depend on the 3 momentum p, not on the energy. Because energy depends on the momentum. So if you change the measure, it should depend on the 3 momentum p. That is first thing. That I hope you agree. But what about all these factors? These factors are very important that I can show you later if you want. This is what we are doing is Lorentz invariant. We are doing everything by obeying the rules of special theory of relativity. So I cannot deviate from special theory of relativity. So if I want to change any sum over p by an integral, you know in statistical mechanics, right? When you replace summation over k by an integral, you need to put in a density of state factor, g of e dt or gp dt, something like this. This is similar to this. You need to put a proper integration measure, and since we have to obey the rules of special theory of relativity, this integration measure better be Lorentz invariant. If it is not Lorentz invariant, then there is a problem. And you can show that this measure is a Lorentz invariant measure. If this was not there, then it is not Lorentz invariant. So everything should be Lorentz invariant. Without this, it is not Lorentz invariant. But this thing, as of now, if you look at it, you cannot say that this is Lorentz invariant or not. So the disadvantage of this is that it is not manifestly Lorentz invariant. By that, what I mean is that if you look at it, you cannot say that it is Lorentz invariant, but it is actually Lorentz invariant. So it is not manifest Lorentz invariance is not there, but it is actually there. So if you replace this sum over p, you have to replace it by a measure, and this measure is Lorentz invariant. So let me just write it down. This is Lorentz invariant measure. This is very important. Lorentz invariance. So what we have shown is that this function s that we have derived now, this is basically a very simple function of this form. So if I say that x is basically x2 minus x1, x is this, then this function s of x is integral d omega p e to the power of I p dot x. But this is the same as integral, sorry, this is d omega p. This is the same as e to the power of minus I p dot x also. Why? Because s of x is symmetric. S of x is minus s of x. This This clear?
আচ্ছা শুনুন একটা, এই J1 যে এগুলো কি আমরা অরিজিনালি লোরেন্স স্কেলার ধরে নিয়েছিলাম?
এগুলো লরেন্স স্কেলার।
সেটা
ফাংশন তো অর্ডিনারি ফাংশন,
একটা নাম্বার।
তাহলে নাম্বার মানে লরেন্স স্কেলার, লরেন্স স্কেলার এবং রিয়েল, রিয়েলিটিটা খুব ইম্পর্টেন্ট। যে এক্সটা
এটা মানে উই ডিমান্ড ইট টু বি লোরেন্স
ইনভেরিয়েন্ট করতে হবে, কারণ আমরা প্রথম থেকেই মেট্রিক রেখে স্পেশাল থিওরি অফ রিলেটিভিটি মেনে করছি সবকিছু। লরেন্স ইনভেরিয়েন্ট থাকতে হবে। আর ওমেগা পি স্কয়ার ডিসপারশন রিলেশনটা, ওটা তো স্পেশাল থিওরি রিলেটিভিটি ডিসপারশন, সো ওগুলো থাকতে হবে। আচ্ছা, এইবার আসছি আপনার টাইম অর্ডারিং এর পয়েন্টে। নাও দ্য টাইম হ্যাজ কাম টু ডিসকাস টাইম অর্ডারিং। So let us discuss this thing. So you can see from here, this was e to the power of plus ip dot x, but by symmetry I am writing it e to the power of minus ip dot x করে লিখলাম। Okay, the thing is that here if I assume that x is what? X is t and x vector, right? But t is basically what? T is basically t2 minus t1, কারণ x হচ্ছে x2 minus x1. So now if I say that t is greater than 0, if t is greater than 0, then you can see that this term will be e to the power of minus I omega p t plus something, right? And this corresponds to the positive energy. So for t greater than 0, this case I will say that this s of x, that is d omega p e to the power of minus I p dot x, this I will call it to be some g plus. This is a Lorentz invariant amplitude. This is by definition. G plus is by definition equal to this for t greater than 0. And what about for t less than 0? For t less than 0, you can show that Sx is basically d omega p e to the power of this, e to the power of I p dot x for t less than 0. And this thing I shall define it to be g minus. This is just by definition. You can actually show that s of x with plus ip dot x instead of minus ip dot x with t less than 0 is basically, you can define it to be another Lorentz invariant amplitude where g plus and g minus are actually different. This is just two-line algebra. If you want me, I can show you, or if you at the end of the lecture you can ask me, I can just derive it for you. It's not that straightforward, but it's not that difficult also. So if you bear with me for this part, then you can now write down a general Sx, which is true for all t, whether t is greater than 0 or t is less than 0. And that you can write it down in the following way. So আবার আমি রিপিট করে দিই তোমাদের জন্য যে Sx, this thing for t greater than 0 is g plus and for t less than 0 is g minus. So the full Sx for all t, whether t is greater than 0 or t less than 0, should be something like this. What is this? This is a theta function. Have you seen this theta function? Heaviside theta function. This definition is basically theta t is equal to 1 for t greater than 0 and it is equal to 0 for t less than 0. And there is also a value for theta at t is equal to 0. That you will not usually get in the books. It is basically half. Also a value you will get in some many body physics books that it is half. So good, I don't require this, but I require this definitely. So you can see that this, the way I have written s of x for all t, now this has some time ordering. This fires only when t is greater than 0. So this, and this is multiplied by g this. This function has been defined for t greater than 0. When t is less than 0, this is 0. And when t is greater than 0, this part is 0. This fires only when t is less than 0. At t less than 0 জন্য s of x হচ্ছে g minus. Okay, so now I have been able to write down a function s of x which holds for all values of t, t greater than 0, t less than 0, right? By using, so this is a kind of time modeling that I have done. So if you look at this expression, this is called Heaviside theta function. So let us now look at this expression s of x, and I shall do some little bit of algebra now. So this is s of x theta t. What is g plus? G plus is d omega p e to the power of minus I p dot x, right? And then plus theta of minus t integral d omega p e to the power of plus I p dot x. Is fine. So now this is equal to theta of t. Let me break this thing out. This is basically d omega p. This is e to the power of minus I omega p t plus I p vector dot x vector. I've shown you how to decompose this. P dot x, p dot x is what? P dot x is by definition t mu x mu. So that is equal to p0 x0 plus 3I xi. So that is equal to p opore 0 x opore 0 p opore I x opore I at the cost of a negative sign because of the signature, but this is equal to omega p, and this part is c vector at x vector. So I get this. Now look at the second term. This is theta minus t d omega p e to the power of I p dot x. This is I omega p into t, and this will be what? Minus I p dot x. Second term is this. Is clear? Now what I shall do is the following. Okay. So now what I shall do is the following. Here theta t, this is equal to d omega p. This I can write it down as because t is greater than 0 in any case, right? So I can replace t by mod t. Mod t is always greater than 0. And what about the second term? Theta minus t d omega p e to the power of t is less than 0.
So minus I omega mod t.
So this will be minus I omega p mod t minus I dot x. Is that all clear for everyone? So this becomes, since t is less than 0, I replace t in this term. I replace t by this. Not replace, I equate it to minus mod t, and in this term I replace t, I equate t to mod t because t is greater than 0. Clear? So now this, let us look at this term.
We can remove the theta now, right?
You cannot remove the theta now.
We cannot.
No, let's keep the theta. Theta is always there. How can we remove?
No,
Remove it.
because we have enforced the.
No,
value
no,
of
no,
t.
no. Reinforce. It's like delta function. When you have enforced the delta function, do you remove the delta function?
No, no, no.
Then
Ah,
here, you can always enforce this thing. But you cannot. This is not equal to this. This is blunder. This is in chess language. This is this. Question mark. This is blunder. Not even dubious. It's completely wrong.
integral করলে হবে
Integral করলে হবে। Integral তো আমি দিই। Integration তো আমি দিই। Okay. So now Just look at this term. This term, you remember, this is d cube p. So what you can do is you can replace p. Now I'm replacing, not equating. I replace p by minus p. I make a change of variables. So if you make a change of variable from p vector going to minus p vector, what happens to this integral? This becomes plus. What happens to the measure d cube d omega p? This becomes d omega minus p. But d omega minus p is the same as d omega p. There is a 3 volume, right? So nothing happens. P going to minus p, everything is same. So nothing happens. So very good. So if p going to minus p, this becomes this thing. So now you can see the beauty here. Your what you wanted to remove the theta function, that will happen. See, now you will get theta t. You wanted to get rid of this theta function, right? So this term and that term is common. Both are same terms. So now you can write this as this d omega p e to the power of minus I omega p mod of t plus I p vector dot its expression. But what is theta t plus theta of minus t? It's 1. So you only have these expressions. So now you have got rid of the theta function. So this function s of x that I have defined in this way is basically equal to what? Let me write down this beautiful expression here. This is basically e to the power of minus I omega p modulus of t plus I. This is what you have. Clear? Okay, so but now there is another trick that I want to show you. That is very crucial because what I wanted to prove, I have not proved it yet, but now I shall prove it. You see that this is basically what? d3p by what? 2 pi whole cube 2 omega p. Now, usually in mathematics, what do we do? If you are given an integral, you compute the integral and get an answer. Now, I'm going to do a reverse trick. The reverse trick is that from the answer, I'm going to convert it to an integral. And you will see, you will be able to write this down as so this expression that I've derived here, this one, this is equal to this. Here, how many integrations were there? 3 integrations over momentum. But here, this integral is basically what? This is dp0 d3p vector by 2 pi whole 4. So I have introduced another integral over p0, and p0 integral is from minus infinity to plus infinity. Only the p0 integral. d3p is over all momentum space. So it is already minus infinity to plus infinity. And I have this I by p square minus m square plus I epsilon e to the power of minus I p dot x, where I have a limit epsilon going to 0 from the positive side. Epsilon is approaching 0 from the positive side. Okay, this is something known as Feynman epsilon prescription. You need to have this to make this integral convergent. Otherwise, it will not converge for this particular metric. So why I am claiming that this thing is this was integration number 3 integrations, but now this is basically 4 integrations. So I have gone from the answer to the integral. What it means is that in this integral, if you perform the p0 integral, you will get back this. To perform the p0 integral over here, so in this integral, p0 and p vector, they are independent. They are not on shell. They are not on shell. They are independent variables. So in this integration, if you perform the P0 integral from minus infinity to plus infinity, you will land up to this answer. So that means that this particular answer can be written in this form. Now this is completely mathematics, no physics here, no physics here. This is an exercise in complex variable analysis, and nowadays you learn complex analysis in BSc, right? So that is the problem. So you have nothing to learn in MSc. So
Just to mention, I can understand, but in the denominator,
Hmm.
I epsilon,
Hmm.
how do you explain that?
given মুছে দিলাম এটা। আচ্ছা ডিনোমিনেটরটা আমি জিজ্ঞেস করেছেন ভালো করেছেন p স্কয়ার মাইনাস m স্কয়ার হোয়াট ইজ p স্কয়ার p মিউ ঠিক আছে তাহলে এটা হচ্ছে p0 প্লাস pi মাইনাস m স্কয়ার p0 টা কিন্তু এখন ওমেগা p নয় এটা ইন্ডিপেন্ডেন্ট ভ্যারিয়েবল অফ শেল So this is now p0 square by metric আমি তুলে দিলাম p0 আর এটাকে আমি লিখলাম p vector square minus m square. But what is this part? This part is precisely p0 square minus omega p square. তাই তো তার মানে কি বলছে this integration has poles at p0 is equal to plus minus omega p. So if I want to do the p0 integralটা কোথা থেকে minus and plus infinity, so minus infinity to plus infinity. So the poles are where at minus omega p plus omega p. So when you come from this side arrow, you will face the poles. So what you do, you want to shift the poles to the right. So that is why you put a plus epsilon with epsilon going to 0 from the positive side. So that will put the poles in a precise way that this integral will be contributing in a way that it will give you this answer. If you do the complex integration, ওই 1/2 omega p টা বেরিয়ে আসবে এবার now as an aside you can understand why is this d omega p Lorentz invariant measure that you can understand very carefully very easily from this analysis because its origin is coming from Lorentz invariant things. D4p, this is D4p. D4p is manifestly Lorentz invariant. And if you, so it is manifestly Lorentz invariant. So if you do the P0 integral, you get d omega p. So it must be Lorentz invariant because it comes from a Lorentz invariant. So as an aside, you can understand that thing also. So what we have got is the following. We have obtained so what we have shown is the following. Sx is basically equal to integration over d4p by 2 pi whole to the power 4 I by p square plus I epsilon. This is obviously limit epsilon is going to 0 from the positive side. Ip dot x. Is that clear? So I have shown that s of x is basically equal to this, and you know, because we have already calculated this, this is basically d omega p e to the power of minus I omega p mod p plus I e dot x. You know already this. We have shown that. We have done a reverse engineering to come from this to this thing. And why we have done this? This is very crucial. Why have we done this thing? We have done this thing precisely to show a very important result. A very important thing. What was my aim? To find the function s and to show what that function s is. It's a Green's function. So that is why I have come to this form. Because you will be able to see that this is a Green's function. Very easy to see now. Why is that? So let us, so this is your answer, right? This is your thing. So let us operate on both sides of that equation by this thing. So this will give us box plus n square. I will tell you what box is. E square minus n square plus I epsilon e to the power of minus I e dot x. Okay, box is the D'Lambertian operator by definition. I have put an x here because it's a derivative with respect to x. So this is basically del mu, right? This is what box x is. And what is del mu, by the way? I have confusion with this also. It's del x mu. Okay. So if you operate with this on both sides, the right hand side, this is an x operator, right? You can put it inside the integral. And if you put it inside the integral, it is not going to act on this factor because this is a function of p. It's only going to act on this factor, right? And so you will get d4p pi 2 pi whole 4. When it will act on this factor, you will get precisely p square minus n square plus I epsilon with a minus. So you'll get. So let me just write it down. I minus p square minus n square plus I epsilon p square minus n square plus I epsilon e to the power of minus I p dot x. This factor comes when this operator acts on this part. So what happens now is that it cancels this. And what you get is minus I integral d4p pi 2 pi to the power of 4 e to the power of minus I. And what is this? This is basically 2 pi whole to the power of 4 delta function. So 2 pi, this factor cancels. You get delta 4. So this actually proves that this function is really a Green's function. Because Green's function, how many of you know Green's function? Green's function you know, but it is not taught in the BSc, right? Green's function is a function which basically you have actually learned Green's function in electrodynamics, but you have not realized it. Green's function is basically a function plus minus potential. It satisfies this kind of an equation. So it basically means it is a function on which, if an operator acts, it will give you a Dirac delta function. That is what a Green's function is. So what I've proved now is that this function s of x, apart from this factor of I, this factor of I has come due to some conventional causes. You can divide this s by this factor I, and you can conveniently get a function which only has a minus, not this I factor. That can be done in this case. So this function is a Green's function.
Sir, in that step where you go from the integral to the result that we had of d3p, how do you know that the integral should have the exact form p square minus n square plus I epsilon in this? Because I can have
Which one?
this integral that you are defining, d4.
D4p.
In d4, yes. So you are saying that this, on integrating the zeroth component, should give us the basically integral that we had. How do we know this has this exact form? Because
if you integrate, you will get that answer.
So it's basically reverse engineering.
No. My question is that this is assuming the Klein-Gordon field equation. But I can
No, you have not. No, you have not assumed anything. You have not assumed any Klein-Gordon field equation. I have not assumed anything.
No, because okay.
You have not assumed anything. What you are saying is that this s of x that I wrote down, this is your answer, right?
Mm-hmm.
This actually follows from this integral. That is what I have said. I have not assumed Klein-Gordon equation.
Because here the box plus n square and epsilon we can ignore. That is the Klein-Gordon operator we can say. And
This is the Klein-Gordon operator. So now you can say that, okay, forget about Klein-Gordon. Forget about Klein-Gordon information. just remember one thing, that the g of x that I have found out here, the s of x that I have found out over here, it is basically the Green's function of this operator. But now from your knowledge, you know that this operator is basically the Klein-Gordon.
No, like what I was claiming was like, let's assume that I don't know initially, and I assume some terms like plus a square plus b square instead of plus m square. That will also give me that this also holds as a Green function.
No, it will not hold as a Green's function. It will hold only for this operator. Other operator, if you put a Dirac operator, no, it's not a Green's function. If you put anything other than, if you change the coefficients here, it will not be a Green's function. Dirac operator, it will not be a Green's function. If you put a higher derivative operator, it will not be a Green's function. This function is a Green's function only for this operator. Only for this operator is a Green's function.
I'll have to rigorously prove, then only I will be able to.
No, this is not a matter of proof also. You get something, right? You get some s of x. And what I've shown you, that this s of x is a Green's function for this operator. Forget about your Klein-Gordon wisdom.
No, like here we insert this I epsilon. We don't have that in the field.
That I epsilon you can forget. I epsilon also I've just put in for proper regularization purpose, for defining the poles. Forget
like
about
I was saying, like if we had something a square plus phi square type of a term.
A square plus
phi. So m square we have m square phi square. Let's say we have something.
No, no, you don't think I have not introduced any phi.
I did not introduce anything. Yeah,
there is no m square phi square term. M square phi square will come out. Will come out.
Okay.
It will come out. The beauty of everything is that there is no phi here.
Exactly.
There is only j.
There is only
j. There is 0 minus. There is 0 plus and 1 p. There is no phi and no field so far. Field will come. Field will come. If you give me some more time, then I can show how fields will come. There is no field here. What you have shown is that my claim was that this function is a Green's function, but Green's function of this operator. This is indeed a Green's function of this operator. There is no phi here. So for you are thinking of in terms of m square phi square. There is no phi here. So,
this formalism is true for both spin zero and spin half particles, right?
No, it is not.
So far,
No, it's not true for spin half.
It's not. So
spin half
in the very beginning,
spin half to Dirac operator. Dirac box operator.
That's all. Initially, we are taking the particle to be spin zero particle. The one particle, so that has to be.
It mentioned absolutely. I agree with you, but to start with, you will not start with the difficult thing. First, you have to think. This is the simplest thing. This spin zero particles. Scalar, একদম ordinary numbers. ডিরাক করতে গেলে কি করে করতে হবে আমি এখনো ডিকোড করতে পারিনি সুইঙ্গারের বই পড়ে। It's very difficult.
সুইঙ্গারের বই তাও করেছে।
ডিরাকে আছে কিনা আমাকে খুঁজে দেখতে হবে। নিশ্চয়ই আছে, কারণ ডিরাক ওখানে এই সুইঙ্গার সমস্ত কিছু জিনিসপত্র করতে হবে, মানে সব করে বইগুলো আমাদের দেখতে হবে। ডিরাক ফিল্ড কিভাবে করছে সেটা পড়েছে, নিশ্চয়ই আছে ওখানে, কিন্তু ডিকোড করা ডিফিকাল্ট।
ইলেকট্রন তো স্টাডি করতে হবে,
ইলেকট্রন স্টাডি করতে হবে,
ইলেকট্রনের অ্যানোমালাস ম্যাগনেটিক
ইলেকট্রন স্টাডি করতে মানে আমি করেইছি, ডেফিনেটলি করেছি। Okay, so I'm still within my time limit, right? But I will take some more time if you allow me, or if you say it is enough here, then I can stop. Anyway,
what
so
is
my
your plan now? What are you going to show?
Our plan actually অনেক একটা খুব বিউটিফুল। দেখুন আমি এই রেজাল্ট দেখাতে গেলে না আমি খুব মানে I really enjoy myself. That is why I do all this thing. So there is a very beautiful result that I can show you, but it will take some time, but not much time. আমি নিজেও জানি না কতক্ষণ estimate. I have no estimate of that time, but not more than maybe half an hour. I can show you that result. But let me just finish this part. So what we have obtained is the following. The result that we have obtained is for, mind you, now let me again come back to physics. So I have shown you everything: particle creation, particle destruction, as well as particle propagation. And propagator in physics, when you go to MSc, you will learn that propagators are basically Green's functions. All propagators are Green's functions. In statistical mechanics, we call it two-point correlation function. In many body physics, you call Green's function. Then you call other names are also there, propagator in quantum mechanics and so on. So what we have shown is the following. We have shown the following result. This is equal to 1 minus half integral d4 x2 d4 x1. আমি at least মানে ওই রেজাল্টটা যদি ডিরাইভ না করি, I will tell you what the result is.
That's good.
I will tell you the result. So this is 1 minus half this. This is j of x2. Now I will replace s by g because this is a Green's function. I have proven it to be a Green's function. This is x2 semicolon x1, and then this is basically j x1. But mind you, this result that I have derived now, the result that I have on board for weak source. So weak sources physically creates only one particle. It only creates one particle. Now let me come to the important result, strong source. Strong source. So strong source, I will just read it off from my notes. Let us please write it down. Consider a strong source J divided into a large number of small independent weak sources. Consider a strong source J divided into a large number of small independent bracket লেখো uncorrelated weak sources. ঠিক আছে?
তাহলে J1 plus J2 plus এর উপরে যেতে হবে।
Additive. Additive. Large number, in so this alpha is equal to sum from 1 to n and limit n goes to infinity. N is very large. N is very large, so small number of small sources. These are small sources, and they are completely independent from each other. This basically means that d4x, d4x prime, j alpha x g x2 করে দিয়ে এটা x করে দিয়ে এটা x semicolon x prime j beta x prime is equal to 0 for alpha not equal to beta. Alpha not equal to beta hole this is 0.
They are uncorrelated.
They are uncorrelated. Alpha is equal to beta hole same source, so they are
They will non-negative.
they will be non-zero. But if it is unequal, then it is 0. So this is what I mean by uncorrelated sources. So I can write the following equation now. For strong source, therefore, I can write it down. Write the following thing. This full J is basically product over alpha 0 minus J alpha 0 plus. Okay. Product over all alphas. So I take all J1, J2, J2 and product go to infinity. But what is this thing? This is basically product over alpha. This is 1 minus half integral d4 x2 d4 x1 j alpha x2 g x2 semicolon x1 multiplied by j alpha x1 clear? I've just substituted this for j alpha, the expression that I have derived for a weak source. I've substituted that expression, and this product symbol, all of you are familiar, right? Product means product of this. Product alpha is equal to 1 to n means এটা থাকবে 1 এর জন্য এটা 2 এর জন্য প্রোডাক্ট হতে হতে যাবে। So this is the famous Euler product symbol. Now just this is equal to can write it like this. Alpha x2 g this j alpha x1. These steps are, you may find it a little bit difficult mathematically, but I will prove it. Dhore naw. If this can be actually written down, this thing can be actually written down in this way. So this is question mark exclamation. Dubious. You may think that sir has done some goof here. Maybe this is not correct, but this is actually correct. So now you can write this thing as e to the power of minus half summation over alpha beta d4 x2 d4 x1 j alpha x2 g x2 x1 j beta. This step is not at all dubious. This is absolutely correct because you use that uncorrelated step. Alpha not equal to beta, all the cross terms will fall off. J1, J2, everything will be 0. So what will remain is only summation over alpha term. So this is fine. I have used the physics here that the sources, different sources are uncorrelated. Now the thing is very simple. This is summation over alpha and summation over beta. Means in longhand, this means basically this, right? So now you put in the sum inside. What is summation j alpha j alpha? This is the full j. And similarly, this is also full j. So this is the result for a strong source. For a strong source, this amplitude that I have written is basically equal to this exponential. Now let me clarify the dubious step. This step to this step. So let me take, say, product alpha is equal to 1 to n, and I call this part as, say, 1 minus some x to the power of alpha. Because what does this mean? And I call this to be, say, y. What does this mean? This basically absolutely 1 minus x1, 1 minus x2. Now the best way to prove this is to take a log of both sides. So if you take a log of y, then what will happen? This will become log of 1 minus x1 plus log of 1 minus x2. That is equal to summation over alpha log of 1 minus x alpha. X alpha is basically this, the two j's. So you can write this approximately as summation over alpha x alpha with a minus log 1 plus x expansion for small x less than 1. So this is approximately this, and therefore the result follows immediately. Log y is equal to this, therefore y is equal to e to the power of minus summation over alpha 2. Right? So we have two results. This is the weak strong source result, and the result has an obvious and nice interpretation of a particle being created at x1 due to the action of a source, followed by its propagation from x1 to x2 and its destruction at x2 by the source acting for the second time. So this completes the whole picture of weak sources and strong sources. কোনটা বলে?
আপনি যেটা বললেন এখানে।
ও লাস্ট মানে লেখা বলাটা, এই যে রেজাল্টটা যেটা বার করলাম এইটা, this result has a very nice physical interpretation. It means this amplitude, vacuum persistence amplitude, is basically nothing but the creation of the particle due to an external source at x1, then the propagation from x1 to x2, and then the destruction of the particle at x2. This is the physical meaning of this result.
So, I mean, I had one question. I mean, that is related to the question that I raised earlier. That is, now this being a strong source, can't it produce more than two particles?
Now it will produce two particles.
So now we'll have to probably, I mean, modify your all theory for more particles.
Now R45 মানে
Just add two particles. I was taking all those
এইটা two particles এর জন্য রেজাল্ট, এটা for many particles. This is a result for many particles. Now this source, এটা এখন আর mild source নয়, strong source. It will create many particles. Now your theory automatically accommodates many particles.
The only thing we are looking at zero particle at the initial time at minus infinity, and no
It is something
in between you can have number of particles.
It is something like generating in mathematical terms in group theory. What we do, we for a finite transformation, we build the finite transformation from an infinitesimal transformation and then make a product infinitely many times. Then you get the group generator. This is similar to this. Now this theory is a theory, or actually where the source is a strong source, it will create many particles.
But non-interactive.
But non-interactive.
Non-interactive.
Still it is non-interactive. It is real, but it is free. The theory is free. Independent particles, because the sources are uncorrelated. With uncorrelated sources গুলো uncorrelated মানে হচ্ছে sources গুলো যে particles গুলো create করছে তারাও free, তারা non-interactive.
I have a question here. You have used standard Green integral or the Schwinger's Green integral?
Standard
Standard Green integral or Schwinger's
standard what integral?
Green integral.
Standard Green integral or
Green integral.
or the Schwinger's Green integral. So basically, in standard what we do, we usually write a line integral about a curve to a double integral about a plane. But where does it come?
No, there is nothing to do with what you have learned in your BSc, the vector calculus, Green's theorem. There is no Green's theorem there. There is no Green's theorem there. So let me just explain this part a little bit nicely. See, you had an integral like this, right?
Yes.
By some factors, 2 pi whole cube I am not writing. I am just writing this thing. And this is nothing, this has nothing to do with any Green integral or anything. This is not Green's theorem. Okay? I am writing this thing as d3p by 2 pi whole cube. This 2 pi whole cube. And then another, I am putting in another integral. Okay, and then I'm saying that okay, fine. Instead of this, I have this as my integrand. My integrand is e to the power of minus I p dot x. You expand it in the same way that I have shown you, but now the p0 component is off shelf. It is not omega p. It is not related to p vector. Fine. So here you will have a p0 integral. If you do the p, and there is, and this is probably it, what I have over here. If you do the p0 integral over here, right? And I think I have a factor of p square minus p square. This I must have. I have this factor in the denominator. Now, if you do the p0 integral only, not the p integral, because my aim is not to do the d3p integral. My aim is to do p0 integral. If you do the p0 integral, what is the p0 integral? The p0 integral is basically something like this: p0 by 2 pi minus infinity to plus infinity e to the power of minus I p0 t divided by p0 square minus omega p square. This, so it tells you that the p0 integral has a problematic thing. It has poles on the real line, on the line along which you are integrating. It has poles. Because at p0 is equal to omega p, the integral diverges.
So what we call this, sir? This is Schwinger's Green theorem, or this is general?
This is no Schwinger theorem. This is Cauchy. This is complex analysis. This is Cauchy, much before Schwinger. This is nothing to do with Schwinger knows all this stuff, but this is not discovered by Schwinger. This is Cauchy, Riemann, and other mathematicians, Laplace, Euler, and people like them. Okay, this is going much back. So you have an integral which has poles along the line in which you are integrated. So if you want to do this integral, you can do this integral, and you can show that this integral has a convergent value. Not all integrals have a convergent value, right? Because you know that these integrals are already, even যদি suppose there is no pole, then also this integral is problematic. Why?
It has a oscillating term, the E is
No, not because of that reason. Not because of that reason. Suppose this term is not there, then also this is a problematic thing.
Oh, it's minus infinity to plus infinity.
Absolutely. Okay, we actually are not taught these things in mathematics very carefully. And physics people should actually know these things. This integral, this is an improper integral. This is called an improper integral because the limits are from minus infinity and plus. Any one limit, if it is infinity, it is an improper integral. So this is already problematic. So improper integral, you are not sure whether this integral will converge or not converge. So that is one problem. On top of that, you have an integrand which has poles along the line on which you are integrating. So for that, you have to invent some new mathematics now, and that mathematics is complex variable analysis, which you will learn in your MSc. And if you do that, you will. But actually, they don't understand.
This is basic residue theory.
Residue theory পরে কিন্তু বোঝে না একটু ওভারডোজ হয়ে যায় বিএসসি তে একটু ওভারডোজ হয় সেমিস্টার টাইম
আর সেমিস্টার বলেও না কিছু জিনিস জানেন তো মানে কিছু জিনিস আছে যেগুলো অত ইয়াং এজে শেখার তো দরকার নেই আর বুদ্ধিটা পাকলে তখন
অ্যাকচুয়ালি এটা ওদের তো ফোর্থ সেমে আছে ততক্ষণ অতটা ম্যাচুরিটি আসে না
মানে সেকেন্ড ইয়ারে পড়ছে
সেকেন্ড ইয়ার একটু মেকানিক্যালি করে
হ্যাঁ মেকানিক্যালি
So another thing we can do here is we can convert this to a Euclidean integral and then take an analytic continuation. Why
that is again hi-fi stuff, don't do that. You are absolutely right. You can convert it, this is a good way. You can convert it to an Euclidean integral by weak rotation, find the answer, again anti-weak rotation, go back and find out the answer. That's the way. Feynman actually tried to do all these tricks.
Yes, because this epsilon thing is, you need to know the convergence of the integral.
That is very easy to find out. You give me 20 minutes, I will tell you how to do it. Very easy, very easy. But you are not taught in the correct way. That is the problematic thing. If you do mechanically, you will not understand. But why epsilon should converge from the positive side, it is just a matter of 2 minutes. It's not a big deal to understand. Anyway, so now your question, if you perform this integral, you need to put in the poles in the proper place, and that is why I put a I epsilon with epsilon going to 0 plus. Now you will ask me why sir, why not 0 minus? There is a particular reason for that. You want the Green's function to be a causal, a Feynman kind of a Green's function. So for that you need to put a 0 plus kind of thing. So that will give you a Feynman Green's function. There are various kinds of Green's function. The Whiteman is much later, but the first Green's function that all of us should learn is the retarded Green's function. Retarded Green's function appears in electromagnetism. That is a causal Green's function. What is causality? Why causal Green's function? It basically tells you the cause cannot precede the effect, right? There is a principle of causality. So retarded Green's function is a causal Green's function. Now you have an advanced Green's function, and there is a Feynman Green's function. And Feynman Green's function is this one. This is the Feynman Green's function. So you have, it's a combination of both kinds. So you can basically show that this thing, when you do the analysis, you will get this result. This is the crux of the thing, and you show that this is a Green's function, and then for strong source, you get a result like this. Okay. Now just let me end with a beautiful result that I have done in my calculations, but I just want to tell you. I want to find out the interaction energy between the sources. What is the interaction energy between the, now everything is strong. See, my goal was to find the strong thing, but to come to the strong thing, I had to start with the weak thing. That was a trick. Okay. Now you can show the following thing, that if you calculate, now you want to say, I told you what this physically means, but you want to say, okay, can I compute something like this, which you have already learned in quantum mechanics? Given any amplitude, how do you calculate probabilities? Mod square. Mod square is the probability density of probability. So I want to calculate this. And if it has to be something related to probability, it better be less than 1. Now you have this expression in front of you. Go back and take it as an exercise, calculate this. Take it as an exercise. And if you do this calculation, you will be able to show that this has a very nice structure. This is given by e to the power of minus d cube p by 2 pi whole cube 2 omega p mod j omega p e vector mod square. If you calculate from this expression, if you calculate the mod square of it, you will see that this is equal to this. Now this definitely therefore has a probabilistic interpretation. Why? Because this quantity is less than 1, and for anything to have a probabilistic interpretation, the quantity better be less than 1. So this is indeed less than 1, e to the power of minus x, for x positive is less than 1, right? And therefore you can interpret this. Now quantum mechanics. This as the probability density of creating a particle with momentum p, and that momentum is on-shell momentum, where omega p is related to p. Probability density of creating a single particle with momentum p, the probability density. Why? Because it is integrated over d cube p by 2 pi whole cube, this factor as the probability. You can give an interpretation to it. You can first calculate the mod square, and now you can give an interpretation to this. Fine? Good. And the last thing that I want to tell you, okay, just exceeded 15 minutes. Let me just write the result now. The result is, you can ask the question that whether, see, this is the quantity that we calculated. This is the result for it. Now, obviously, you can see that this thing is a real number, right? This thing is a real number. But the Green's function, this thing is not a real number. This thing, if you remember, it is e to the power of minus I p dot x integral and so on. So it's not a real number. So this thing obviously is not a real number. That is what quantum mechanical probability amplitudes are. They are not real. The mod square things are real, right? Mod square things are real. Probability densities are real, but amplitudes are not real. They are complex numbers. So this is basically a complex number. Since it is a complex number, it basically tells us that this has a phase. This has a phase. Here we calculated the mod square of that quantity. So when you calculate mod square, all information about the phase has been lost. Now you ask the question, can we get some information, or what information can we find out from the phase of this quantity, of this complex number? What information can we extract from the phase of this quantity? And in order to do that, in order to extract that information, we have to just assume that Jx is basically J of x vector. That is, it is a static source. And then the beautiful result will come out. Assume that the source, so far I've been assuming that it is not a static source. It is a function of t. But now you say that it is a static source. It is independent of the time t. And then if you calculate this particular quantity, you will get this to be from here to here. This is a long derivation. We'll find this. So you can see that for a static source, this probability amplitude only has a phase and nothing else. So if you take a mod square, what will be the answer? It will be 1. So it basically means that there is no particle creation.
Sources to vary.
There is no particle creation. Nothing happens. Only when particles are created, then that f of j comes in. And so particles are created, particles are destroyed, and things like that. But here, for a static source, there is no particle creation. And you can see from the structure, since there is a minus I here, you can interpret this E physically as the energy, as the interaction energy. And this energy has a beautiful structure. You will see that this energy epsilon can be written as half. You'll be able to derive it. This will be basically dq x1 vector, d3 x2 vector, jx2 v x2 minus x1 g x1. So what the static source has done, it has actually increased the phase of this quantity for an infinite duration. It keeps on increasing the phase of the quantity, and this epsilon is basically given by this expression, where the v of x vector, basically e to the power of minus mx vector divided by 2 pi. Please write down this result. It's a beautiful result that you can derive. This object, you start calculating from here, for a static source is basically equal to this thing where epsilon is given by this. It is as if the two sources are talking with each other, or is in the presence of a potential V of this, and that potential is basically a Yukawa potential. And it is for this potential that Yukawa won the Nobel Prize. See, this beautiful potential comes out automatically. Such a beautiful result. It is this result for which Yukawa got the Nobel Prize. The sources are talking with each other in the present. So the sources are basically, there is probably V of this, there is a minus sign here. Minus sign. So basically it means that this V is actually negative. So the sources are attracting each other in the presence of a potential which is the Yukawa potential. You take the m going to zero limit, it goes to the Coulomb potential. So they are attracting each other, and in the way when they attract each other, they are basically exchanging particles of mass m. And this is the result for the interaction energy of the two sources.
But the static source cannot produce particles.
Particle to produce করেনি, কিন্তু they are interacting.
Particles.
এরা পার্টিকেল এক্সচেঞ্জ করছে নিজেদের মধ্যে দিয়ে আবার সব যা খুশি হয়ে যাচ্ছে, মানে রিয়েল পার্টিকেলস তৈরি করছে না।
Two particles, so two nuclei. That is a source here, right? And Yukawa first derived it for nuclear forces, meson theory.
মেজন থিওরির জন্য করেছিল। মেজন থিওরির জন্য পাই মেজন।
Now, if we put it in this Schwinger's formulation,
পাই এখন পাই মেজন আর you will not be able to discuss from here. But what is the thing is that this Yukawa kind of a potential naturally comes out from your analysis.
from Schwinger's analysis.
From Schwinger's analysis.
When the source is static.
When the source is static.
But static force, as you just showed, I mean,
there is no real particle.
Only phase is there.
Only phase is there. No real particle production is there.
But then, how to? I mean.
So physically, you can think that this is an effective potential that is being created among these sources. And since this effective potential is being created, the sources are attracting each other. The static sources are attracting each other. So
now it has become I mean, the sources are interacting. Previously, you were taking sources are non-interacting, right? So,
let me put it in this way. See, here also you have a J, you have a J, you have a G, right? This also has the same structure. J, G, some V, right? So it is also some function. Once again, some function. Now you are giving an interpretation. এটা একটা ইন্টারাকশন এনার্জির মতো একটা জিনিস হয়েছে, সোর্সের মধ্যে একটা তৈরি হয়েছে, ইন্টারাকশন এনার্জির মতো তৈরি হয়েছে, এবং সর্ট অফ অ্যাজ ইফ ওরা একটা ইউকাওয়া পটেনশিয়ালের মধ্যে এফেক্টিভ থিওরি হিসেবে আপনি ভাবতে পারেন। ইউ আর থিংকিং অ্যাজ অ্যান এফেক্টিভ থিওরি, when it is sort of in an effective Yukawa potential and it is exchanging particles of masses. The sources are exchanging particles of masses. মানে এদের মধ্যে যদি অ্যাট্রাকশন একটা থাকে, যেমন গ্র্যাভিটিতে দুটো মাসের মধ্যে, তার মানে আমরা এখন জানি যে it is exchanging particles, বা two charges, they are exchanging some particles, and therefore the electromagnetic interaction is taking place. The photon is the mediator for electromagnetic interaction. In gravity case, the graviton is the mediator. So now you can think in this way that there are two sources which is mediating, which is talking to each other in some way. আমাদের প্রথমে যে ইন্টারপ্রিটেশন দিয়ে শুরু করেছে, ওখানে সোর্সেস গুলো সত্যিই নন ইন্টারাক্টিভ, সবকিছু নন ইন্টারাক্টিং থেকেই এখানে এসেছে। এবার আমি আবার একটা ইন্টারপ্রিটেশন একটা দিচ্ছি। This is a matter of interpretation. Now, whether you take this interpretation, you like it or not like it, that's a separate issue. But the beauty is that you get some potential. If you at all call this function as some potential, then that potential precisely has a form like the U power potential. This is something a very nice result. And so far, I have not talked anything about the fields. Fields, you will get all the fields from here, from this result itself. So what I have shown from this result, I have shown your mod square. So it is a probabilistic interpretation. For static source, the phase has some information. So two things, and where are the fields hidden? The fields are hidden here. This is the third thing, the last thing. The fields are hidden here. You have this quantity. Calculate this quantity. And you will be able to show that this is precisely
And what is this Cardi D? This is that measure that was there.
this is a functional measure. It basically means this quantity is a functional of J. You make a Fourier transform of this quantity, e to the power of I d4x jx phi x. This is like a functional Fourier transform, jx phi x, and integrate over all possible functions J. So this full integral is a functional Fourier transform, and this integral is a functional integral. And you can completely make sense of this functional integral in terms of ordinary integrals. You can make sense of that. If you do that, this computation is just 3-4 lines. You can show that this is equal to some quantity like this, where this s of phi, is basically half del mu phi minus. This is the action of a real scalar field in quantum field theory. Action of a real scalar field. So if you
Phi x is a field.
phi x is a field. So you have now extracted the hidden field. The fields were hiding inside. Now you have found out the fields from this source picture. You calculate this, make a Fourier transform, functional Fourier transform. You get this. S is the action for the field, real scalar field. If I had started with a complex J, তাহলে এই অ্যাকশনটা বেরোতো কমপ্লেক্স স্কেলার ফিল্ড। Automatically you would have found out complex scalar field. So this is the third important result, and you have now this is the quantum field theory picture. And what in usual quantum field theory, what we do is the following. Usual quantum field theory, we actually start from this thing, then make a functional Fourier transform. So what we do is very simple. Usual quantum field theory, we take this, this will be a minus. is phi plus I this, all possible fields phi, functional integral, and you get the thing with which we have been working so far. So you start from this e to the power of is phi plus this thing, integration over functional integral over all possible fields, get this quantity, the vacuum persistence amplitude. And this quantity is actually very important because this is the generator of the correlation functions. You start functionally differentiating with respect to the source, you will get all the propagators of the field, all the correlation functions of the field. So I would like to stop here now. Thank you.
Any questions from the students?
Yes.
So is there any specific advantage of this theory? Like in quantum field theory, we run into problems like divergences, UV, IR problems, and a lot of other issues as well. Does this theory manage to resolve those in any possible way?
To see, when Schwinger did it, he worked in the regime of perturbation theory. Okay. And there are issues of renormalization and things like that. I would not say that this theory, to me, for the present day particle physicists, this theory may not be so advantageous because this theory is calculationally very, very difficult. This is for a free theory because you get the action for the free theory. Now, if you want to treat interactions with source theory, then it will become very difficult. So there is as such, no advantage. But you can do many modern kind of things, such as there are certain things like gauge gravity correspondence, ADS-CFT duality, and many other things that you may be able to get a very nice picture from this source theory. This source theory, my hunch is that source theory may play a very nice role in the advanced modern subjects which you have now. Because this particular theory was only done by Schwinger. Nobody else, nobody else worked with it. It is not that nobody else worked with it. Nobody else even dared to look at this theory because this was such a complicated mathematical theory. Now I would say that it is mathematical because you have to do a lot of algebra and very difficult algebra. This is very simple algebra.
In more or less sense, this is very similar to what we do in QFT as well. Like, for example, we were to treat a
See, the main means advantage of having a quantum field theoretic picture is that, first of all, fields, you realize the fact that fields are fundamental. They are fundamental objects. They are there. Even in source theory, there are fields. The hidden fields are there. The second thing is that when you apply the techniques of quantum field theory in particle physics or other areas of physics, mainly in particle physics, you have the advantage of working with some diagrammatic things. For example, the Feynman diagrams that you don't have here. You can have, but Schwinger never liked the Feynman picture, Feynman diagrams. Schwinger never did Feynman diagrams. He did not like these Feynman diagrams. So he never did this. And you will find, if you go back historically, the 3 volumes of books that he wrote down, that was from 1987 onwards, 1987 till his death in 1994. So at the later years, he actually wrote down, formalized this, and wrote it down in the form of 3 big volumes. But nobody actually looks into it. But I can tell you with guarantee that if you look into it, you will definitely get some very nice insights and something you may discover on your own, something new, if you are able to learn
Did not
something.
Schwinger have some students who would
carried on his work.
Schwinger তো খুব একটা student ছিল না, ওদের student নিত না। Schwinger চুপচাপ নিজের মনে কাজ করে যেত। কিন্তু একটা জিনিস যেটা খুব মারাত্মক Schwinger's কাজে আপনি যদি দেখেন, it's a quantum effective action. Quantum effective action. Schwinger actually gave it in the realm of quantum mechanics itself. Well, Schwinger quantum mechanics, if you read Schwinger quantum mechanics, it is completely different from the textbooks that you find. It's written in a totally different way. For example, if you read Weinberg's quantum field theory,
3 volumes.
3 volumes, it says last volume the for na porai bhalo. But the
Last
first
2
two
volumes.
volumes are just completely, he does it in a different way. Weinberg's quantum field theory, masterpieces. কিন্তু ওয়াইনবার্গ কোয়ান্টাম ফিল্ড থিওরি প্রথমেই পড়া উচিত না, কিছু বুঝতে পারি।
So now let's.
Okay.
Yeah.
দেখাবো 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 তাহলে চলো চাটা নিয়ে আসি, তুমি চলে এসো, আমি তোমাকে দেখা
And
দেবো।
also students, we need to discuss with you about the student session. So please wait here for 10 minutes. Once we will decide it, then you can go for the.
তুমি চাটা নিয়ে
for the
এসো, আমি
tea.
দেখিয়ে দিচ্ছি।
Yeah, sir will be waiting for you.
Okay.
So formally we thank sir for delivering this wonderful